So we're gonna still talk about online algorithms. I hope you recall last time it's about how to make decision, and you cannot revoke that decision, and it's still gonna be guaranteed to be good, no matter what you know the future or not. Okay, but what we're gonna do today is to have a more principled way to design online algorithms. Okay, and we're gonna use LP. So you have seen two ways to design algorithm using LP. One is LP routing, which is which has this template, right? You model the problem with integer program, relax it to LP, and then solve the LP, and then route it to the integral solution. So that's the one template. And another one is to design a primal dual algorithm, where primal dual algorithm. So in the previous class, we basically does anyone recall some vague template of this kind of algorithm?
Formulate the problem as LP, take the dual of it, and then do an algorithm that pushes the constraints of the dual to be tight, so that it ensures that the solution will be feasible, and then add that constraint to our set of solutions.
Very good. So have a problem. Now you just look at both primal and dual LP, and the algorithm will maintain both solution, primal and dual solution, right? The algorithm will maintain feasible dual solution, and then update a primal variable on the one that if the corresponding dual constraint is what?
Tight.
It's tight. Yeah. So this thing will allow you to be able to bound the cost of primal by the dual solution. Yeah. So this is one particular way but the general point of this is that you maintain both primal and dual solution, and you try to reason about the cost of primal based on your dual solution. This is one way to achieve that, to bound the cost of your primal solution with the dual solution, with your dual solution. But when we said that it's primal dual algorithm, people usually actually just take it more generally. That is, it's just some algorithm that maintain both solution and try to reason about primal using dual. Okay, so today we will use primal dual in this loose sense. So it's basically in this step. So if you remember when we use LP routing approach, every step here we have seen, but when we try to solve the LP, we just said, okay, use a black box, just solve the LP. But today it's in the online setting, and we will need to solve the LP ourselves. Now the question, how to solve the LP ourselves, we will solve the LP using some primal dual algorithm. Not quite this, it's not quite doing this exactly, but it's maintain both primal and dual solution. Okay, so that's the plan for today, and let's go. Okay, so let's recall online ski rental problem, right? It's a problem where you go to play ski. On each day, you can rent and pay $1 per day, or you can choose to buy the ski equipment and pay $B. Okay. But if you buy, then that you don't need to ever pay again. You don't need to rent again. But you don't know how many days can you have for playing ski. Okay. And on each day, you need to decide to buy or rent. Okay. And the goal is to minimize the cost, right? And we have seen two algorithms from last class. A deterministic one that is too competitive. Yeah. Can you recall what's the algorithm for two competitive one? Yeah.
You rent for B days and then buy.
Exactly. Rent for B days and then buy. And then we have seen that, okay, if the adversary is oblivious, you can go beyond 2. You can get below 2 using some simple randomized algorithm. And we're going to see how to get better today. This turns out to be the optimal algorithm. I will not prove why it's optimal, but it's the best, actually. We're just going to see the upper bound. So the first step, right, is to model the problem as an integer program. And that is basically like, what we're going to do is this. This is, again, like when you have a problem, it's not too clear. There are many ways to model it as an integer program. This is one particular way that will work. Okay? And what we're going to do is this. Just create X to indicate whether you're going to buy or not buy. Okay? And Zi is to indicate whether you're going to rent on day I or not. And with this variables, now you can write it down like as this integer program where you want to minimize the cost. The cost is you're gonna buy, like you're gonna pay B if you buy. And on each day, you're gonna pay 1 if you rent. So this is the cost. And what you'd have is that for each day, you need to either buy or rent on each day I. So I hope you're convinced that this really kind of capture the problem. But note one thing, that is, this is an online problem. So it means that actually this integer program is not a fixed one. There's gonna be like a new constraint per day coming to you. Like on the first day, the constraint for day 1 appears and you need to certify it. Then you don't know if there is the next day, but if there is, then the new constraint come and you need to define day 2 too, right? So the new constraint is given to you per day, and you must certify it before the next day come. You don't know when it will stop. And another point is that, so this is like one point. Another point is that the decision that you make is irrevocable. So you can only flip from 0 to 1 and not vice versa. Okay? So like if you have bought the equipment, you cannot revoke it. Yeah. Every variables here can only flip from 0 to 1, not 1 to 0. And with this 2 additional constraints here, now it really captured the problem. These 2 constraints kind of capture the online nature of the problem. Okay. So that's the online integer program. Online IP. Okay. And next is to relax, right? Which is we're just gonna throw away the integral constraint here, integrality constraint, and we just allow it to be fractional. Okay, so that's like the obvious thing to do in the offline setting. We just relax this to be like at least 0. But when you are in the online setting, what would you guess, like how should we like capture this thing? Yeah.
Maybe those variables can only increase, they can't decrease.
Yeah, we allow it to be fractional, can be 0.2, 0.3, but it shouldn't ever decrease. This is how like a natural way to capture this aspect, right? It's monotonically increasing. Yeah. It's good. So this is what we're gonna do, right? We're gonna relax it to online LP relaxation, which is just relax the integrality constraint. And now the difference is that each variable now can only increase, but you can increase it fractionally. What you have the same as IP here is just that like the new constraint come one by one like before, and you don't know when it will finish. Good. And now, once we have this LP, I can also talk about the competitive ratio or like the approximation, and let's call it competitive ratio of how you solve the online LP. Okay. So suppose that there is this online LP given to you, and there is some algorithm that solves this, like find a feasible solution to this LP. We said that that online algorithm have competitive ratio something if the cost of the solution at the end is small compared to the optimal offline cost. So what's the optimal offline cost? It's just the cost when like the whole LP on every constraint is given to you, and you just solve it like from scratch. So compare this optimal offline cost to the cost that you solve this online LP when each constraint is coming to you one by one, and you can only increase each variable as well.
Could you explain the optimal offline cost just one more time? I don't
Sure.
really understand it.
So optimal offline cost is the cost of like, it's just look at the LP when you have all the constraint given to you.
So we know how many days?
You know everything.
Okay.
Yeah.
Then, but it won't be as good, because if we know how many days, then we can just like develop like a trivial algorithm to say that like, oh, I'll buy it at the beginning, or I'll just rent for this many days. Will it be better than that, or?
So it can be fractional. So it could be better than the optimal integral solution.
Okay.
So this is like, it's both fractional and offline. Yeah. So you can like, now our goal is to compare yourself to like the algorithm that is both offline and fractional. Okay. So this is the goal. Okay. Question up to now? Right. So now our goal is to now design an online algorithm to solve this online LP such that it's as good as the offline fractional cost. Okay. So we need to solve the online LP, right? Previously, when in the offline setting, again, if you want to solve LP, just call some black box and solve it and get the get an optimal solution, optimal fractional solution. Now it's online, so there is no like a black box that you can just use. And we're gonna just derive our own algorithm, okay? And yeah, so we're gonna use this, what I said, like an online primal dual method. And generally speaking, it's just an algorithm that maintains both primal and dual solution, and then use LP duality to argue about approximation ratio or like competitive ratio. So sometimes I say approximation, sometimes I say competitive. It's kind of the same concept, right? Yeah. Okay, so it's primal dual. So the first step, right, is to look at the LP and write down the dual. Okay. So what's the dual? So, well, what we do is like, when you try to write the dual, you just create a variable, right, for each constraint. This is called yi, and then you derive the dual. Again, I will not like derive it for you. If I encourage you to like do it at home and convince yourself, or like at least try to convince yourself like quickly that it's a dual. Yeah. Okay. But let's still like interpret this a bit. Okay. So what do we have? We have that we have like the variable y on the dual, right? And each y, for each day, the yi is at most 1. And we have that like the sum of all the y is at most b. Okay. And we just want to maximize the yi. Okay. So if this is an offline solution, if this is an offline LP, it's quite clear that like you can just set like a b of this guy to be 1, and then the solution is b. Okay, it's not a super interesting LP, but note that this one is an online LP. The constraint is kind of coming to you one by one, so it must be some online aspect on the dual too, right? So what would that be? If each constraint on the primal come to you one by one, what would that correspond to? What happened to the dual LP? Yeah.
Each variable?
Each variable will kind of appear one by one.
Yeah.
Yeah. Good. So on each day, P will get new constraint, and the dual will get new variable. Okay. This is like what will happen. And now the strategy that we try to do is this. Let me describe the algorithm right away, actually. Maybe do it like this. Good. Okay, maybe it's too small. Okay. Maybe just this. Okay. So initially, I just set like x to be 0. X is like whether to buy or not, but x is now fractional. Okay? And on each new day, we just check if x is 1 or not. It's still less than 1 or not. Okay. If it's more than 1, it's at least 1, then you don't have to do anything. Everything is satisfied from now. But if it's less than 1, what we're gonna do is that, okay, the new variable y, I, for day I come to you. I'm just gonna set it to 1. This is just for analysis, really. Okay. It will have nothing, like doesn't affect anything below. So I just set yi to 1. And then the next step is I set zi to be 1 minus x. And so it means what? So x plus ci is now at least 1 for the I. So at this point, the constraint, the new constraint is just satisfied. Okay. And if it's just this, if we don't do anything more, then x will keep being 0 at every step. If I don't do anything, if there is no if this step is not there, then it means that what we can do is just to rent every day, right? Because x is 0, and then we just say we set zi to be 1 on every day. Yeah.
I actually have a question on the dual, if that's okay, if we can go back.
Yep.
So I know you said, or you're talking about like it being online, right, which like restricts it. But I think even for the online algorithm, wouldn't you just set yi equal to 1 until the sum of your current yi's are b, and then you'll just set all of the other ones to 0? Isn't it like a trivial solution at your way?
Yeah. So actually you see that the way to solve this online dual LP is actually trivial, like you said. Like each variable come one by one, and you just keep setting each guy to be 1, 1, 1, 1 until b of them is 1. Then you just stop, like you cannot do anything more. Okay. So solving this one in the online setting is going to be trivial. But this one is not trivial. We're gonna just use this for analysis. It doesn't tell, like the fact that we know how to solve this easily doesn't tell us how can we solve this easily. Because the online nature of these two LP are very different, right? One is you have new constraint. One is you have new variable.
So it's like, so you sort of do you kind of lose like strong duality when you're looking at it in an online setting, or?
Yeah, we not hope to get exact algorithm here. Yeah. So you see that we just use this for analysis. Yeah. Okay. So back to algorithm, right? Yeah. On each day, I just set yi to 1. And just rent to the extent that I satisfy the day I. And then what I'm gonna do is like I'm gonna increase x fractionally. So the idea is like on each day, the extent to what I want to buy should increase and like should increase again and again, right? So what I'm gonna do is to increase x. And the way you should think about this is that, like, how much you increase x is like you increase x kind of with some factor, 1 plus 1 over b. So it's kind of increased exponentially with this rate. But I will need to have this term, like this additive term, for like to make the math nice. But the way you should think of this is that without this additive term, x start with 0. So if I just keep multiplying, it's just stay at 0 all the time. So I just need to start with some small thing. Once I start with some like one small additive factor, after that I can like it just become meaningful to like increase exponentially. Okay. But yeah, you can think like x start with like a 1 over b something and increase exponentially with this rate. But the math just looks a bit nicer if I just start with 0 and then set it to be like this. Okay. Is the algorithm clear? Okay. Now our analysis will have 3 steps. The first is that we're gonna say that okay, we have the primal solution is feasible at any time, and then we're gonna try to bound the cost of primal by the cost of dual. So this is the primal dual step, right? This is what makes it primal dual algorithm. We bound the cost of primal using the cost of dual, and then we said that the dual solution is feasible. Sorry, here I mean delta p. Here I mean the increase in the cost of primal is bounded by the increase of the cost of dual with some factor at any time. So that's the plan. Let's start with the first one. The first one is kind of trivial. Just because. Sorry. Actually, let's be convinced about this now. This one is trivial, right? Because on each day I just set Ci to be 1 minus x. So every constraint is satisfied. Okay. This two it's not going to be clear why it's true. But suppose that it's true, then let's try to prove that we get the good algorithm. Okay. So again, the second point here is that on every day, the total increase in the cost of primal, this is increase in the cost of primal, is at most 1 plus 1 over c times the increase in the cost of dual. Okay, this is what I mean by second point here. Okay. And if we have all these three, then I claim that our algorithm must be 1 plus 1 over c competitive. So the reason is what? The reason is that if on every day the primal cost is at most the dual cost times this much, then our primal solution at the end is just going to be at most dual solution, the cost of dual solution at the end times this much. But now, if our dual solution is feasible, it's like a valid solution, then the dual solution, which is of this packing problem, is going to be at most the optimal packing value of dual, the optimal dual value. This is true if our dual solution is feasible. And then by weak duality, op of dual is at most op of primal. So so in picture, basically we have this, right? We have, this is the optimal solution for the op of a P and op of D. P and D here, I mean P and D at the end, at the very end. The offline optimal of P and D. They must be the same. Okay. And we're gonna maintain some primal solution here, right? And then and the primal solution will be above the optimal LP. And then we're gonna also maintain the cost of the dual solution. We're gonna maintain dual solution. And what we're gonna say is that this thing, right, is actually at most 1 plus 1 over c cos of dual our dual solution. Okay. So actually it should be like this. And we have this thing. Yeah. So we want to bound this thing, but actually we can bound this thing. So everything here is up to 1 plus 1 over c factor. So it means that these two guys must be within 1 plus 1 over c factor. Okay. So do you agree that all remains is just to prove this step and this step? Okay. So let's try to prove that. Okay. So the first step is trivial. I skip. The second step is this. That the cause of the change in the cause of primal is at most the change in the cause of dual. So there are two cases. If once x is at least 1, then we do nothing. We already basically buy the ski and nothing changed. So the cause is just, the change in the cause is just 0 from now. But when x is less than 1, what do we have? Basically, if on day I, x less than 1. So what we do, right? First thing is that we just set the new yi to be 1. So the change in the dual objective is 1. Right? We set yi to be 1. So that increase the objective. Like this thing increased by 1. So we get this. So now let's analyze how much, like right now, my goal is to prove that the change in the primal solution is now at most 1 plus 1 over c. Okay. Let's just try to analyze it. Well, what's the cause of like the change in the primal solution? The change in the primal cause is just b times x new minus x old plus ci. Right? Because the objective is just, yeah, the objective, we want to minimize like x plus sum of ci. This is the objective. And on day I, how does this increase? Just increase by ci, and how much you increase x times b. Right? So this is, I just write this as, yeah, the change in x, which is b times change in x plus ci. Okay. What's ci? We said, maybe I just write it clearly. Yeah. Maybe I do it myself. I do it here. Zi is said to be like 1 minus x old. then x new is said to be distinct, right? X old times 1 plus 1 over b plus distinct. Okay. So we can just analyze what is how big is this thing. So it's now just calculation. So let's see. Well, x old like b times x new minus x old is just like b times x old over b plus 1 plus c over b. Basically, like I just look at this, which basically just kind of cancel this thing. Yeah. This is equal to this one. So this is just x old plus 1 over c. Okay. So it means that b like this thing plus this thing, the sum of these two is just this plus this. The sum is then the sum is 1 plus 1 over c. Okay. So we just proved that the change in the cost of primal is going to be exactly 1 plus 1 over c, which proved this. Right? Question about this? Just calculation, right? Okay. Good. So good. So at any time, if the cost of primal increase, the cost of dual will increase too. Okay. And the cost of primal will not increase too fast compared to dual. And now we just want to say that like our dual solution is feasible. So right now, just let's think how does our dual like solution looks like. It's just on each day we just set the new yi to be 1. Next day the new yi is 1. And to make it feasible, what do we need?
Need the sum to be less than or equal to b.
We need the
Right.
sum to be less than b.
So we just basically need that loop where we like set it to 1 to only run at most b times.
Exactly. So the only way to say that this is feasible under our algorithm is to prove that there's going to be at most b days before x is at least 1. Right? That's the goal. You agree? Like we just want to prove that x is at least 1 before, like after b days. And why do you think that's the case? That should be some really intuitive, like just some intuitive argument for this. Why it should be the case that x should be at least 1 after b days.
Well, x correspond, like if x is 1, that corresponds to like buying, and x is 0, that corresponds to renting. So if we buy, like, so that means that x should be like we buy it after some amount of days, and that corresponds to what's happening in the dual.
Yeah, like so that's kind of we have seen from last time that one algorithm that is too competitive is that to buy after B days. Okay, so, but that is about that algorithm. Now I want to know, like, from our algorithm here, can you give me some intuitive argument why it should be the case that X is at least 1 after B days? Yeah.
I mean, I'm not sure if this is different from what Ron said, but like, this algorithm has to be like at least as good as the two competitive algorithm, right? So like after B days, if that algorithm has bought, and like if we've rented for more than B days, then we're going to be worse than that algorithm. So
Yeah. So that is the reason, given that you know that this algorithm is better than the previous one. Okay, Blake.
So it's LP, right? And we're updating our X value,
Yeah.
right? Up by a little bit
Yeah.
over time.
Yeah.
Right? And after, like, given that update step that we have, we should, by B days, we should reach one, because we're minimizing X times B plus the sum of the ZIs, right? And we can't decrease X either, right? Because
X never decrease.
X never decreases,
Yeah.
because by our online setting.
Right.
So then, like, after we increment B to a certain, after we increment X to a certain point, that constraint we have, X plus ZI will always be 1, and that way we don't have to increase Z anymore ever again.
Yeah. I mean, okay. So what I get from you is that okay, X never decrease, but there is like so. I think what I want to tell you is basically this: we increase X in some specific way, which is we increase X with this exponential rate. On what rate? Something like 1 plus 1 over B. Right? So if you increase with like the rate of 1 plus 1 over B, you kind of basically expect that after B days, it should be at least 1. That's like how you can think about it. You increase with this rate. So after B day, it should be like 1. Yeah. So, okay. So is that intuitive? And let's try to analyze it, right? Okay. So we're going to prove that after B days, X must be at least 1. So, okay. That's the intuition, like X grow exponentially with this rate. And so after B days, what we're gonna get is something like this factor kind of composed for B times. So it's like this thing to the B, which is something like E, which is more than 1. That's how, like, informally I think about it. Okay. But how you gonna like prove this formally? You can even show like the closed form of X from the formula. And the closed form is gonna be just this. I would not prove it here, but you can just write it like this. And you can see that X kind of grow exponentially in, like, it makes sense. Like X grow exponentially in 1 plus 1 over B after B days. So this is going to be a number of days. Okay. And there is a rate C here, which also makes sense because like we set X to be 1 plus 1 over B times X plus 1 over C, right? If C is huge, then it means that the additive factor here is small. So it should be like the X should be small if C is huge. And if C is tiny, then x is big. So it's kind of x is proportional to 1 over c. Okay. But anyway, we get this closed form. Okay. Now, it means what? It means that after b days, x is exactly this. And if we want that x to be at least 1, so we can just choose, as long as we choose c to be less than the numerator, right? Then we're gonna have that x is at least 1. So let's choose c to be exactly this numerator. How big is this thing? Yeah, this is basically, again, like, this is just e to the 1 minus, like really close to e to 1 over b times b, which is just e. So basically c is e minus 1. So we get that our commutative ratio is just 1 plus 1 over c, which is e over e minus 1. Okay. So just by setting c to be like small enough, then you know that like a dual solution is feasible. You're gonna finish like after b days, and you get this commutative ratio. Okay. So far, what have we done? We relaxed our problem to online LP and solve the online LP like competitively with this factor. It's not exact algorithm. What's the last step? To round, yeah. Oh, you see a bit, yeah. Okay, it still counts, yeah. So you round it, right? Right now, what you have is like, you have some fractional value of x and zi. Okay, but we want to basically decide when we're gonna buy something. Okay. Right now, like the way what happened is like x will just keep increasing over time until x at least 1. And I'm gonna define something. I'm gonna like let xi to denote the increase of x at day I. Okay, so like after day 1, xi is this. After day 2, x increased by this much, so this is x2. After day 3 is like this. So x keep increasing, and the increase on each day is, on day I is xi. Okay. And like x4 could be like, could increase the interval of 1 a bit. Okay. Because, yeah. But anyway, I just gonna concentrate on the interval from 0 to 1. We know that after b days, like if this is xb, then like we're gonna finish, like it's gonna exceed 1. Yeah. Okay. So far we need to design the routing algorithm. Do you think this routing algorithm will be randomized or deterministic? Yeah.
Randomized?
It must be randomized, right? If it's deterministic, we cannot hope to get better than 2. Okay. So what would be like some natural way to randomize, to get a randomized algorithm to decide when to buy? Yeah.
Probability that you buy is kind of how close it is to 1.
Say again?
Probability that you buy is kind of how close it is to 1, x.
Yeah. Maybe be more specific, like, yeah.
Probability x.
Probability x, I.
Yeah.
So you say like we're gonna buy at day I with probability xi, something like that.
Yeah.
Okay.
Or you can use
Anyone else?
I think we can first random points in this segment and set x to be one. It first reach this point.
Yeah. So like pick like a random point in this segment. Let's say I pick it here. If it's here, then what again?
Then we set x to be one. It is x3.
Set x to be 1 at day 3. That's what you mean?
Yeah.
Yeah, exactly. So yeah, just like that, like kind of just pick a random point in the 0, 1 interval here. If it land on like an interval of x3, then buy at day 3. If it land on the interval of x4, land by at day 4. Yeah, this is the only randomized step, but we need to be randomized. Okay. By the way, note that, yeah, so I pick tau uniformly. If tau is in xi interval, by at day I. Note one thing, this algorithm will, like this description will make no sense if we allow x to be decreasing. Right. This makes sense only if like a xi is at least 0. Because yeah. So this routing algorithm rely on the fact that our LP is monotone. Yeah.
So I'm trying to like connect sort of, I guess, the online, because it kind of feels like here we've already been to day 4, kind of. So are we? Or I guess all the xi's are. I guess it's deterministic. 'Cause it's based on B and C, which are determined. Okay.
Yeah, like everything so far really is deterministic. So you know all the xi like from the beginning actually.
And then so just ahead of time we say, okay, we're gonna buy on day
Yeah.
3 or
Yeah.
randomly.
Yeah. So okay, that's the routing algorithm, and let's try to analyze it. All right. And good. How it works is like this. Just expected cost at day I is just b times the probability that we buy at day I plus the probability that we rent at day I, and the probability that we buy at day I is just the probability that tau is in xi interval, which is b plus which is just xi. The probability that we don't like we rent at day I is the probability that like tau wasn't in the interval for like tau is not in any xj for all j. So if we're gonna rent at this day, if we rent on day I, it means that tau is somewhere here. So what is this probability? Well, just 1 minus all the sum of xi, sum of xj from j equals 1 to I. But what is this? This is just exactly CI. So, okay. So the cost is basically this much, right? And then, so when we sum this thing up, it's just bx plus sum of CI. So it means what? It means that our expected cost, our expected integral cost is just the same as the fractional cost in our online LP, exactly. Yeah. but the fractional cost of our online LP is something like 1.58 times opt. So that's how, like this is like the routing scheme that you don't lose any factor. But what we lose is in the fractional world actually. Okay, so that's the algorithm. Okay, questions? Let's try to do it on another problem. Okay. This is set cover problem. We have seen this many times. There are m many sets. There are n many elements. Okay, and we want to find the set cover T. You choose a bunch of sets such that it covers everything. But now it's online, so now it's going to be the case that each element is reviewed one by one. We don't see the future element that haven't been reviewed. And then what we're going to do is like we're going to choose some set to cover the element. But if we choose to include set S to cover things, then the set S need to be in your collection forever. Okay. So in picture, like it's like you have S here, right? And then you have like some elements here, something like this. If you remember this picture, then the new element come. And if suppose you choose this set already and choose this set, if this set happen to already contain this element, then you don't need to do anything. It's already covered. But if this new element is not covered by any set yet, now you need to choose some set to cover it. Maybe you choose a new set here to cover this thing. And this new set must be forever there in your solution. Okay.
So we need to maintain a set cover at the end of every iteration.
Yeah. So you keep increasing set cover in your solution, and it must cover everything at any time. Okay. So we have seen algorithm that is like log n approximation in the offline setting. What we're gonna see today is that like if we pay another log m, not log n, another log m factor, it can work even in the online setting. Okay. So the same step, right? I'm gonna go a bit more quickly. So we just model it as a IP. We have seen this IP before. The difference is just that the new element come one by one. The new constraint come to you one by one. Okay. And you can only flip from 0 to 1, not 1 to 0. Next, relax it. So throw away the integrity constraint. Each of the constraints still come to you one by one, but now, okay, it's fractional value. You can only increase variables like before. Okay, so that's the same step. Next, try to solve the LP in the online setting. Okay. So we use primal dual method. Like before, we're gonna maintain both primal and dual solution. And we just use dual solution again just for analysis, right? Okay, so you write down, you have this set cover LP, and write out the dual LP. Let's analyze, interpret this again. If you recall, it's like a element packing LP, right? You try to pack. You have the element variable for each element. You try to put value into element as much as possible, but there is a constraint for each set. like there is a capacity on each set that you cannot put packing value of elements of all the elements in the set by more than one. Okay. So this thing get new constraint per day, dual get new variable per day. Okay. And there is one to describe the algorithm that I'm gonna define one thing. I'm gonna define XE to be kind of a sum of all the set that contains E, sum of XS of all the set S that contains E. So in picture, it's like this. Like let's say that this is element E, right? Element E is basically in some set S1, S2, S3. And I just sum all the XX, SS1. This is so kind of, it's like imagine that if X of E is at least 1, it means like it's fractionally covered, right? So it's kind of measure to what extent this E is covered fractionally. Okay. So the algorithm is going to be simple. It's just this. Initially, I'm just gonna set the value on every set to be 1 over m. Like everyone here, I kind of choose everyone a bit by 1 over m. Okay. And then when the new element arrive, new element E, I just look at, okay, how much, like what is XE? Some of the set I already chose to some extent. Some of the set I might not choose at all. So I just look at XE for this new element. If XE is at least 1, then it's already kind of fractionally covered. So I don't need to do anything. It's kind of good for me already. Basically the constraint here is satisfied for element E. Right? If this is, what is this? This is XE. If XE is at least 1, then you do nothing. The constraint is good. But if XE is less than 1, we will do something. What do we do? I'm just gonna look at all the set that contains me. There's maybe 3 set, the orange set that contains E. And then I'm gonna double the value of all these XS. And then I just set YE to be 1 plus 1. Note one thing, like this one have like the same nature as the last algorithm. That is, you basically try to satisfy the primal constraint by multiplicatively increasing your solution. Okay, you increase it by like some multiplicative factor. Okay, so I keep doing this. Like if it's still less than 1, just double. Keep doubling until X is covered. Like X is at least 1. That's the algorithm. And what YE is basically like try to count how many times you have been doubling for the element E. Okay. Okay. So far, the algorithm is clear, right? And here's the step for analysis. First, we can see that the solution is feasible at any time, and that's clear. We just keep doubling until it's satisfied, right? So the primal solution is feasible. And next, we're gonna say this, that the change in the cost of primal is at most the change in the cost of dual, like before, similar to before. Okay. And lastly, the dual solution is almost feasible. If the dual solution is feasible, then it like this together would mean that we get like an optimal solution, right? Because the cost of your primal is always like total. The cost is at most the cost of dual at every day, and if the dual is just feasible, then it means that your primal cost is at most dual cost, and you're done. You are optimal, but the third case actually says that actually dual is not quite feasible, but it's close to feasible up to some factor. Okay. So I mean, like, y is not feasible, but y over gamma is feasible. Okay. And if this is the case, then we're gonna get like a gamma commutative algorithm. Why? Because our primal solution, the cost of primal solution, is going to be at most the cost of initial primal solution plus the cost of dual solution. This is by 2, right? You start with this cost, and the total increase of the cost of primal is at most the cost of dual. Okay. Now, what is this one? This is just 1. Because you just start by like setting every set to be of size, like the value of every set is 1 over m. So the sum of the initial cost is just like sum over this m times, so it's just 1. Okay. What about this? We know that like sum of ye over gamma is at most of d, because like y over gamma is feasible, so this thing is at most of d. So it means that sum of ye is at most of d times gamma, so this gives this one. Okay. And by weak duality, we get that of dual is at most of primal, and gamma is going to be like log m. Okay. And 1 here is trivially like at least opt, so at most opt. So yeah. So everything here is at most log m times opt. Okay. So now again it's to kind of remain to prove the second and third point. So let's prove it. This first point is kind of easy, okay? Now, the second point here, that the cost of primal increase by at most the cost of dual. Well, like we will do anything if xe is less than 1, right? If the new element e comes and xe is at least 1, you do nothing, so nothing happened. So let's assume that xe is less than 1. We're gonna whenever we increase primal objective, xe is less than 1. But when But what is the total increase of our objective? We just increase by this much, exactly this much, right? Because why? Like we just kind of just double. Like if x is less than 1, what do? We double the value x on each set that contains E. So we increase by like the increase is just by exactly sum of x s of x that contains E. So we double by this, like the increase is basically this one, which is xe, which is less than 1. But how much does this is an increase in primal? Okay. What about dual? Just increase y by 1. So the increase in primal is at most 1. The increase in dual is 1. So we actually get the strict inequality. So lastly, it's just okay. It's just about like I want to say that y over gamma is feasible. To say this, it just means that for any set, right? The sum of all the elements in the set is at most sum like gamma here. Okay. Why this should be the case? It means let's write down what it means here, right? You have like a set S and it contains several elements, right? And then ye1, ye2, ye3, each of these. When you increase y by 1, what happened? You double this guy, right? So, and in the beginning, this guy, this xs in the beginning is 1 over m. And if you double this guy many times, it's going to be more than 1. How many times you need to double so that this is more than 1? Something like log m times. But once this is 1, will it be ever doubling again? No, right? Once this is more than 1, then when the new elements come, the element that kind of that this guy like that is in the set will be covered completely, so it will not be doubling again. So you know that the sum of times that is that like the sum of this thing that count the number of times of doubling, it's just going to be log m. So you get this. Make sense? Okay. Yeah. Yeah. I can just keep. All right. So the last step is just. So okay. So what do we have so far? We have that we solve the LP near optimally up to log m factor. Right. Now it's to round. So let's recall a bit how did we round the LP for this offline set cover, right? If you recall, like, just forget about online for a moment, right? When we like look at the LP routing algorithm for a set cover, what we do is like we solve the LP optimally, and then we generate like a set T1 up to Tk, like make log n copies of this. And for each Ti, we just say that, okay, for each set, include the set into Ti independently with probability xs, right? And then you just return the union of all the Ti. That was our algorithm. And what's the cost? Well, we know that like the probability that S is in Ti is xs, so the cost of the expected size of Ti is just the sum of xs, which is the fractional cost in the LP. So the cost of T, which is a union of k many guys, is just at most k times the expected size of Ti, so which is just log n times the fractional cost. So that's like the cost, but we also show that we also show that after like for each Ti, it might not be set cover, but once after you union log n many of Ti's, then the union is a set cover with high probability. That was our algorithm, right? We want to do this again, basically, in the online setting. But what's the problem? The problem is that when we try to say that we're gonna include S into Ti with probability xs, but xs is not like fixed. Like it kind of keep growing. Like each of xs is like some monotone value that keep growing. So the goal then is to the problem is that we want to do this in online setting. Problem is that xs keep increasing, it's not fixed. But from the analysis above, right, you can convince yourself that it's enough to just try to maintain Ti so that at any time you have this probability that okay, S is in Ti with probability xs at any time. Like if this thing increase, the probability that S is in Ti should increase too. Just try to keep this invariant. If this is true, then everything would work. Okay. What would you suggest? How do you maintain this? How do you achieve this? There is some natural way to do this. Let's say at day 1, xs increased by 0.1. What would you do? Well, if the first day it increased by 0.1, if you just say you're just gonna include it into Ti with probably 0.1.
Oh. Okay.
That's it.
Yeah.
Then it's gonna be in your set with probably 0.1. Okay. Then maybe next day this guy increased by another 0.2. What would you do?
It's 0.3 or just 0.2.
Yeah, maybe try to include it with another 0.2 probability.
Yeah.
Just if it increased by how much?
Oh, okay.
Just with that probability of increase, just put it into the set.
Just increase probability.
Okay. So note that it's not gonna be exactly if you do this. So the algorithm is just here, right? If xs increased by xs t on day t, then include s into your set with this probability. Note that with this algorithm, it's not going to be the case that you get exactly the same here. Why? Imagine that on day 1 and day 2, on day 1, xs increased by half, on day 2 it's increased by another half. Now the sum is 1.
Yeah.
But you still have a chance to not include like S into your solution. But it's gonna be basically with the same order. Actually, you can prove this. That is, with this algorithm, you get that this is order of XS. And it's good enough. So I want you to convince yourself that it's really, you get this order, okay? And once you have this, then just do the same of routing algorithm that you have. And you get a set cover with high probability. And you're gonna pay 1 log n factor and 1 log m factor. Okay, so that's it for today. You see the way to solve online algorithm using LP. Next class is gonna be starting point of multiplicative weight update, which is one of the coolest algorithms. Yeah, see you next time.